So, in the last lecture we were talking about Langmuir-Hinshelwood kinetics and reaction mechanism. So, we are just discussing an example problem which is cumene converts to benzene and propylene. So, that is the reaction which we were talking about last time, and we had seen that the possibility of the different steps, say cumene adsorbs on the surface, that is the adsorption of cumene, and we have already done the cumene as a rate controlling step and determine the rate of reaction. Then second one is the adsorbed cumene on the surface, it transfers into another adsorbed benzene and the propene in the gas phase. So, propene does not adsorb, that is what we assume. And finally, this adsorbed benzene dissolves from the surface and the product benzene comes in the gas phase. So, we discussed this rate equation, the rate of reaction, all of you know now that the rate of forward reaction minus rate of backward reaction, that is net rate of adsorption. Similarly, net rate of surface reaction is forward reaction minus the backward reaction. If you just recall it, this is your surface reaction and rate will be proportional to the concentration of the adsorbed C. So, that is what written here in terms of the concentration, that is K s times theta C. So, theta C is the adsorbed concentration of cumene, and then there was a reverse reaction which will depend on the benzene B sigma and the concentration of propylene in the gas phase. So, the expression comes in the form of the adsorbed benzene concentration and the partial pressure of propylene which is in the gas phase. So, if the desorption is rate controlling, then your net rate of desorption, that was the third step, then it will be written based on this, which is again provided here from this equation. So, B sigma, that is the forward side rate minus the reverse, and you get the expression for desorption of the benzene which is adsorbed on the surface of a catalyst. So, either A step may be rate controlling, B step or C. So, any step may be a rate controlling when you devise a mechanism, right. You need to do some characterization to identify whether it is possible or not, and then you can demystify. So, here in this rate postulation, first step we assume that adsorption is rate controlling, and the second case it is the surface reaction may be the rate determining step, right. So, in that way the net rate, if this is the rate controlling step, then your rate of reaction will be given by the second step of this reaction, which is your RDS now. So, this is your RDS, rate determining step or rate controlling step. So, your net rate, that is R pro cumene, will be written like this: rate of consumption of cumene or rate of reaction for cumene decomposition, that is given something like this. So, theta C and theta B are the unknown of the reaction. So, you need to find out the unknown concentrations, right, which is adsorbed species concentration. For that, because this is the rate determining step, it means this will take the highest time or slowest step of the reaction. So, other two will be very fast or they are assumed to be at equilibrium. So, in one way you say net rate of adsorption of this is 0, and same thing net rate of desorption is 0, or you say that they are very fast and at equilibrium. So, one can very easily calculate now from here a relationship between theta V and theta C, right, that is simply your capital K A adsorption equilibrium constant times the partial pressure of the cumene from the first step, right. Same thing for the third, which is rate of desorption. So, from here also you can find out theta B divided by theta V, and that is again in the form of K minus d P B divided by K d, that is simply P B upon K d. So, from here and here, so whatever you have defined, these can be substituted in this final rate. So, that is what mentioned here, that net rate of adsorption is 0 and you find theta C. So, theta C is capital K, which is adsorption equilibrium constant for this reaction, that is rate of forward reaction is equal to rate of backward reaction. So, adsorption equilibrium constant, partial pressure of C times the concentration of the vacant site. Rate of desorption again, because this is not a rate controlling step. So, again this is 0. So, one can calculate theta B, which is partial pressure of benzene times theta V divided by the equilibrium constant for the desorption of this reaction, right. So, now we can apply the side balance. So, we have already done this. So, theta C plus theta B plus theta V is equal to 1. So, you can calculate theta V from here, because already theta C is calculated, theta B is calculated. So, theta V, which is the concentration of vacant site, is depending on the partial pressure of the cumene and partial pressure of the benzene. So, one can see that if more concentration of these reactant species or the product species is present in the reactor, then there will be some drop in the concentration of the vacant site. So, vacant site concentration is decreasing depending upon the partial pressure, right. So, substitute this value of theta V in your rate equation, which is your surface reaction rate controlling, that we have already defined here. So, one can very easily find out the overall rate of reaction. So, this is the overall rate of reaction, net rate of reaction. So, minus K s, which is already in this expression here, minus K s, and substituted the value of theta C. So, that expression is in the form of theta C, now converted in the form of theta V, and the same thing for the second term of the equation. So, one can just take all these equilibrium constants, say K s and K has been taken out, theta V is again common. So, has been taken out. So, finally, in the bracket is some kind of the concentration difference, right, a difference which is the driving force for the reaction to happen, right, or how far the reaction is away from equilibrium. When the concentration reach to the equilibrium composition, there will not be any chemical reaction, and this is the information which you get from thermodynamics of this chemical reaction. So, this is simply P c minus partial pressure of benzene times partial pressure of propylene divided by K A, K D, K S, which is the adsorption equilibrium constant, desorption equilibrium constant, and equilibrium constant for the surface reaction, right. So, this is the overall rate of reaction, and if this reaction is 0, suppose, right, when you say that the reaction is at equilibrium, then this will be 0, right, and if you write that, then this term which is P c, right, P b P p divided by P c, if I write, that is your adsorption equilibrium constant, or sorry, equilibrium constant for the overall rate of reaction, right. That is what the K equilibrium, because at equilibrium this driving force is 0, then the reaction reaches to equilibrium, this is 0. So, one can very easily calculate this K equilibrium for this reaction, because you know C is equal to P plus B. So, overall reaction is P plus B, something like this, right. So, overall equilibrium constant is nothing but the partial pressure of P at equilibrium times the partial pressure of B at equilibrium divided by the partial pressure of C at equilibrium, and this is the term which is, if you see here, right. So, that is, so this term becomes your K equilibrium constant for the reaction. So, R c, once you substitute the value of theta V also, then this is K s times K A, and in the bracket terms are P c minus P p P b divided by K equilibrium, because theta V has already been calculated like this. So, theta V is substituted here, 1 upon 1 plus K A P c plus P b upon K d. So, this equation is the overall rate of reaction when surface reaction is rate controlling, and I told you in most of the case the surface reaction controls the rate, especially in the heterogeneous catalytic reaction. The third case may be the desorption is the rate controlling step. So, I will quickly go to these steps, because you know now the procedure. So, when desorption is rate controlling, then net rate of desorption is equal to rate of forward reaction minus backward reaction, rate of backward reaction. So, K d times theta B, because benzene is being desorbed, minus K minus d times partial pressure of benzene times theta V, and one can very easily write the expression. If you take K d out, then this is theta B minus P b theta B upon K d, where capital K d is nothing but the rate constant for desorption, that is capital K d is the forward reaction rate constant divided by the backward reaction rate constant. So, that is what written here for the equilibrium constant for the desorption reaction. So, net rate of adsorption we have already seen in the previous calculation. So, theta c is equal to this K times capital K times P c times theta v, and similarly theta b is defined here, and this is again because this time the surface reaction is fast and at equilibrium. In earlier case this was rate controlling. So, net rate was determined based on this, but this time the third step is the rate controlling, this one net rate will be given by this. So, this will be fast and at equilibrium. So, one can very easily calculate from here the theta b, and this is your value of theta b. So, again side balance, because you have to write a relationship among theta c, theta b and theta v. So, which is the total fraction of the sides, which is sum of these 1 sigma of theta I. So, theta c plus theta b plus theta v, that is equal to 1, right. So, one can calculate the concentration of the vacant side for this case also, right. So, vacant side concentration will change depending upon the rate determining step, right. If you have some inert in the reactant mixture, then also it will affect. If inert also absorbs on the vacant side concentration, then this will also appear in the denominator of the reaction, right. So, it means the presence of inert may affect the overall rate or overall kinetics of the reaction, right. So, one can very easily write now rate equation, which is given in terms of the third step, that is desorption. So, K d times capital K surface reaction equilibrium constant, K A adsorption constant, and P c partial pressure times theta v vacant side concentration divided by P p partial pressure of propylene minus P b partial pressure of benzene, theta v concentration of the vacant side, and divide by the adsorption desorption equilibrium constant. So, minus R c can be written and theta v can be substituted here, which is given here in this rate, and finally, this is the net rate of reaction when the desorption controls the rate. So, K d, which is the kinetic constant for desorption, this is the rate constant. So, this is basically a temperature dependent term. In all cases, when you have a small rate, small k, that is deciding the rate of reaction as a function of temperature. The other terms are also depending on temperature, but they are the heat of adsorption basically. How to heat of adsorption, heat of desorption change with surface coverage, right, because equilibrium constant is a function of temperature again. So, this is based on heat of adsorption term, and this is based on the activation energy of the reaction, that is K d term, temperature dependency, right. So, capital this is small k d times K A K s minus this is the driving force. So, that is temperature dependent term times the driving force, which is P c minus P p B b upon K equilibrium, which is written here in terms of this, right, because this, as I told, when the reaction is at equilibrium, overall reaction is at equilibrium, which will be observed from the thermodynamics, that time this net rate is 0, right. And if you solve this, just make it 0 and you will have the same equation what we have discussed before, that is your partial pressure of the this P c upon P p minus P b divided by this is equal to 0. So, this will be your equilibrium K equilibrium, overall equilibrium constant for the desorption reaction, right. So, one can very easily calculate that. So, that is what written here directly P c upon P p minus P b upon K equilibrium. So, that is equilibrium constant for the desorption reaction. And so, one can so this is what how the heat of reaction or delta H or effect of temperature on K equilibrium, one can very easily write it, because this is a function of K A, K s and K d, right. So, basically it will be delta H plus delta H s plus delta H d, heat of adsorption of each term, right. This is from your, because you know K is equal to e to the power minus delta H upon R t, right. So, that is heat of adsorption for equilibrium constant, and basically this is from the want of equation, right, whereas this small k is from the Arrhenius equation, k is equal to k 0 e to the power minus e upon R t. So, basically if I have two terms small k times the capital K, it means the net heat effect, if you take overall internal overall activation energy, it is something like E plus delta H, right, but you know that delta H is much low compared to E value. So, we neglect that and we write just in terms of E, right. So, depending upon the rate constant, which is your, that is what the kinetic term which I am talking here, this is a temperature dependent term here, right, and this is the driving force, that is the concentration dependent term, and third is nothing but the whatever the adsorption term which appears in the denominator of the reaction, right, and that may hinder the overall rate of reaction. So, it means now you have seen that depending upon the term which is available in the denominator, or that may hinder the rate of reaction, right. So, effect of increasing reactant concentration. So, that is the cumin in this case, right, and sometimes you can see the effect of product also. So, when you study experimentally this thing, then you can add some product concentration in the feed itself, right. That is says propylene, effect of partial pressure of propylene, say in this case effect of partial pressure of benzene. So, in the feed, along with feed you add some concentration of propylene or benzene and then again check the effect, right, because already the benzene is there now, it will absorb on the surface if it affects the rate, right. If does not affect the rate, partial pressure does not affect, it means this will not, whatever the different concentration of benzene that is in the feed, the overall rate will not change, right. So, one can postulate these mechanism and confirm them from the experimental result, because based on this the experiment effect of each variables can be studied, right, and that in this case the design of experiment, how many experiments will be required to verify the mechanism, that becomes very important, right. So, either you go with response surface methodology, which is a kind of tool, right, to optimize the number of parameters required, or you do the design of experiment, that is factorial design, which says that if there are n number of process variables, then 2 to the power n will be the number of experiments required, minimum number. So, one can decide the minimum range and maximum range of the variable experimental variables, effect of temperature, effect of partial pressure, concentration. So, all these can be studied by doing the design of experiment. So, here you can see that increasing the reactant concentration, it increase the driving force and the adsorption inhibition term, both term. So, what I am saying, driving force is this term which is in the bracket P c minus P p P b divided by K equilibrium for this third case where desorption is rate controlling, right, and this denominator is representing the adsorption term. So, it means you will see that when you plot a rate as a function of partial pressure of A or concentration of A, then initially it increase and then finally it decrease. So, you will have two regions, in this case, right. So, that is what, because of these terms which is shown here in the earlier section, because of this term here partial pressure, because if I just look at effect of partial pressure of each species. So, P c here, so increase the partial pressure of C. So, initially rate will increase, right, depending upon the contribution of this P p and P c, right. So, accordingly the rate will change, because during the reaction if you have a kind of integral reactor or a commercial reactor, then P p propylene is also forming, right, during the reaction. So, this is also you can see here that it may hinder the rate of reaction. So, what would be the effect of an inert, that is just I have left for thought. So, you just write the, just suppose there is inert also and inert also adsorbs on the surface, then one can write the rate expression for that, right. So, rate of adsorption of inert, that is this is something like that, if the reaction is something like this, C is P plus B, and then you have written the mechanism and suppose nitrogen is added along with this feed, right. So, basically nitrogen is not a reactant, but the presence of nitrogen, the partial pressure of nitrogen can be studied, right. It may not adsorb. So, if it adsorbs, then the mechanism will be different, N 2 plus a star, N 2 star, right, and finally it desorbs. So, one can very easily write down the stuff. So, if it appears in the denominator of the rate equation, or if you see that the effect of partial pressure of nitrogen hinders the rate of reaction, then it means nitrogen is also adsorbing, right, it has some effect, right. If at different partial pressure of nitrogen the net rate of reaction does not change, it means the presence of inert has no role, right. So, this, and it is not only for the inert, but sometimes a foreign element like poison precursor. The different deactivation kinetic models have been developed by understanding this mechanism, that is, if sulfur precursor is present in the feedstock, it adsorbs on the surface of the catalyst, right. So, it will be a like kind of CP poison precursor. So, now the available sites will be less, right. So, when the sites are less, your theta v is low, and then finally, your rate which is proportional to the theta v also. So, it will decrease, right. So, this is what the you have just written it as a thought, that look at that and a kind of FAQ can this is the question which is asked here. So, basically when adsorption is rate controlling, we have already seen minus R c. So, which is K A rate constant for the adsorption reaction, times P c minus P p P b upon K equilibrium. So, this expression we already seen, divide by the denominator which is the adsorption inhibition term, and are reported in the form of partial pressure of propylene, benzene and benzene partial pressure, right. So, this is the first one, and for surface reaction the rate is representing like this, something which is again here. If you look at the driving force, it remains here same, and the denominator term is different, and simultaneously this term which is the kinetic term, that also changes, right. So, here the it is just activation energy of the first, that is E A, right. Here it is activation energy plus heat of adsorption, right. So, E A plus delta H A, heat of adsorption, that is the temperature dependent term. And if it is desorption, then it is again the E d, that is desorption kinetic rate constant, plus the delta H A and plus delta H S, right. So, one can postulate these kind of, that is verify these models. So, model 1, model 2, model 3, and then look at the rate data, and then regress the data, and one can look at that which step is more suitably controlling the rate or guiding the mechanism. So, again one can see that effect of inert, which I have already said last time, right. So, in general the rate is given by a kinetic term times the driving force, that is the difference of concentration, and divide by the adsorption term, and sometimes this may be written adsorption term to the power n also, because in this case if you see, right, the denominator is just the power is 1, but it can be 2 also, it can be 3 also, right. And when you see this kind of reaction rate, this kind, so the power is not 1, rather it may be 2 or 3 also, depending upon this drop, because otherwise if the power is 1, it will go just like a plateau here, a constant line, right. But when it decreases, it means the denominator has more role, or the adsorption inhibition term is dominating at higher concentration of the reactant species. So, that is important here in terms of that in any Langmuir-Hinshelwood type mechanism or Ehlers-Riedel type mechanism, the rate is given by a kinetic term times the driving force divided by the adsorption term, and one can use the softwares like Polymath is one software tool which is available for kinetic study, right. Camken, HYSYS, Origin, MATLAB, right. So, these are used for data analysis or regressing the data, and that can be attached with some optimization tool also, optimization package, and then one can find out the optimal parameters for the reaction, and which will be important for the design. So, Aspen Plus can also be used for that purpose, right, when you scale up the reactors. So, these kind of tools, software tools or application tools can be used for the rate parameter estimation or design of a kinetic reaction. So, we have already seen the data now. So, kinetic terms which are, right, K A, K S K A, as I told, the temperature dependency. So, kinetics means the term which depends on the temperature, rate which will show the temperature dependency. So, based on Arrhenius equation or the how the heat of reaction or how the equilibrium constant change with the temperature, that is basically in terms of delta H, heat of adsorption, right. So, K S K A, and for desorption K D times K A K S, right, for this reaction. Driving force, that is depending on the difference of the concentration. So, P c minus P p P b upon K equilibrium, P c minus P p P b upon K equilibrium, and this is again same. So, when the reaction is at equilibrium, net rate of reaction is 0, right. So, this is what the definition of the this you get from the thermodynamics. So, effect of temperature, right, on this product distribution, that can be changed. If you change the temperature, the thermodynamic results will change, and one can just find out the optimum conditions, right, depending upon the thermodynamics of the reaction and the kinetics of the reaction. So, that one can see that the important thermodynamics is that gives you the idea whether a reaction is possible or not, as I discussed in the beginning, right, and simultaneously the maximum extent of the reaction is also governed by the thermodynamics of the reaction, right. So, equilibrium conversion is suppose 60% at a given temperature, it cannot be changed by changing the catalyst. So, catalyst cannot do that job, right. Catalyst can only enhance these terms, that is kinetics towards that. So, the activation energy of the reaction may be lowered in the presence of catalyst, or changing the catalyst you can do that job better even at a lower temperature, but the maximum limit cannot be changed, which is governed by this term, right. So, at equilibrium this term is 0, right, rate of forward reaction is equal to rate of backward reaction. Adsorption term again, which is a kind of inhibition term and will appear in the denominator. So, that can also for this reaction the different you can see for different cases the parameters are different or adsorption value. So, for one can postulate the mechanism, develop the rate equation for different different set of the rate determining step, and then do the model, that is analysis, that is model discrimination and parameter analysis or estimation. So, same thing for coverage theta c, that is the fraction of the surface which is covered by cumene, one can calculate which is depending on the partial pressure of the propylene, benzene and the concentration of the weakened site divided by Ks Kd, right. Surface reaction case it is this, and for desorption case it is this. So, this is just analysis of one typical set of data which is for cumene reaction we have given, and that. So, for different reaction to reaction these will change, right, and one has to identify. Same thing for benzene also. So, one can see that for adsorption step, for surface reaction and for desorption, right. So, one has to define this depending upon the reaction and rate controlling step, that how the coverage change for a given reactant species or a product species. So, what we have inferred from this, the analysis whatever the mechanism, devising a mechanism which is basically to design a reactor or evaluate the rate data, right, and finally decide a rate of reaction. So, the comments which can be made now, that for a given mechanism the driving force is very important, it is unique, right. You have seen that this is the driving force, the other terms whatever the RDS, the terms are changing here, right, terms are changing here in the numerator denominator in terms of the kinetics and the adsorption, but this does not change, right. The driving force is the unique, right, for a given reaction, and that is what I said is governed by the thermodynamics, right. So, thermodynamics plays a very important role whether a reaction is possible or not. So, this is irrespective of RDS, your driving force does not change, right. The second is the product of equilibrium constant of all step in the mechanism yield the overall equilibrium constant. So, again I said that overall equilibrium constant is what we decide from this, right. You have just written here the equilibrium constant something like whatever the rate expression this term, right. So, at equilibrium this rate is 0, and then do you decide the overall equilibrium constant, right. So, overall equilibrium constant will depend on the adsorption, desorption and surface reaction equilibrium rate constant, right, and that what we have seen. So, when you calculate the overall equilibrium constant, you set this term 0, because that is the meaning of equilibrium, right, and that is what the meaning here is, that the equilibrium constant, product of equilibrium constant of all steps in the mechanism yield the overall equilibrium constant, right. So, whatever the equilibrium constant for individual steps, that is to be checked, and that will give you the overall equilibrium constant. So, adsorption, desorption, surface reaction, and that will give you the idea about the equilibrium constant, that we have seen from the mechanism. Kinetic term, if you look at the rate constant of rate determining step will appear, right. So, the kinetic term this one. So, which is the rate, which one is the rate determining rate controlling step, right, it is that will come here. So, here you see the rate constant for adsorption step has come, here the rate constant for surface reaction has come, here the rate constant for the desorption has come. So, it means this step, if this is rate controlling, as I have already said that the kinetics is something which is giving you rate constant is equal to some pre-exponential factor times e to the power minus e upon r t, right. And when I am writing the step, suppose if you must have learned this, that if a multiple reaction goes like this r plus s, right, then this may have a rate constant k 1, this may have a rate constant k 2, right, and the temperature dependency will decide. If I say that activation energy for this is E 1 and activation energy for this reaction is E 2, and E 1 is greater than E 2, right. So, the if E 1 is greater than E 2 suppose, and if you increase the temperature, then reaction will shift toward this side, right, because high temperature favors the reaction of higher activation energy, right. So, that is important. So, same case is being done here. When I say step is the rate controlling, Rate controlling means that is the slowest step of the reaction, right. So, slowest step means it reaches either high temperature, right, to activate a reaction, or activation energy is high, right. So, if the reaction is low, the activation energy means it can be done at a lower temperature, right. So, that is what the meaning here. So, the rate controlling step, whatever the step rate controls, the kinetics of that will appear here, right, because the second step rate constant is very high compared to the other. This is the slowest step k. When this step is rate controlling, say adsorption is rate controlling, it means its a rate constant order is 0.001 suppose, right, whereas its rate constant order may be 10 and its rate constant order may be 100, right. So, slowest rate is this. So, this is a rate controlling step, right, because rate is controlled by the slowest step of the reaction. When its k is low, it means the rate will be low and that will be rate controlling. So, this is the postulation what we have discussed here, that k p a will not appear in the adsorption term if a is not rate determining step, right. That I think let me just go here for in the kinetic term, the rate constant of RDS will appear. So, that we have seen. So, again how to search a mechanism, that you have to do with different case to case, select different reactions, right, and just for practice you can try define the mechanism and then determine the overall rate, and that will give you more and more understanding about this mechanism and determining the rate equation for different rate controlling step. So, some comments again here, if adsorption of A is not determining, not RDS rate determining step, then k p a will appear in the adsorption term, right. That is what we have seen, that the step which is not the rate determining term, right, that adsorption of A is not RDS. So, it means this k p a will appear in the adsorption term, which is in the denominator, right, and that we have already seen here, that the denominator term here, right. So, adsorption term, this adsorption control. So, this appear, this k p a has not come here, because A is adsorption of A is rate controlling, right. Here surface reaction has not come in the denominator K s, here this term has not appeared in the denominator, which is desorption. So, what does it mean, that the step which is rate controlling will not appear in the, its term will not appear in the denominator. So, that is RDS step will sorry, then k p a, if this is not rate determining, then it will appear in the denominator. If it is not RDS, then it will not appear in the denominator, right. That is what the interpretation which I made. And if desorption of B is not rate limiting, right, if B is not rate controlling step, then P b upon k d will appear in the adsorption term. So, that is what the some postulation which we have defined here, right, the term which are appearing in the denominator. So, that is the second case, surface reaction, right, is the rate controlling, it means desorption of B is not rate controlling, right. So, that term has arrived here. So, this is again the observation which has been made from this, that B is not the rate limiting desorption of B, then P b upon k d appear in the adsorption term, denominator of the adsorption, that is rate reaction. If surface reaction is rate determining, then adsorption term will be raised to the power equal to the number of sites involved in the surface reaction step, and this is what I was talking here, to the power n. So, what are the number of reactant species which are involved, right, which involved in the surface reaction rate controlling, their number will appear here. So, in that case only one reactant is there. Suppose two reactants, suppose if I write A S plus B S gives you R R plus S S. So, two sites are involved now, right, and rate will be the concentration of these A and B, right, A S plus B S. So, this will go square term here, right. So, that is the meaning of this term, that in kinetic term the surface reaction is RDS rate determining step, then adsorption term will be raised to the power equal to the number of sites involved in the surface reaction step, right. So, A plus B, if I write a dual mechanism, then also dual site mechanism, then also the power will come 2 like that, right. So, basically if there is this adsorption, that is rate is equal to kinetic term times the driving force, which we have already discussed, divided by adsorption term to the power n, right. So, that is the value of this. Suppose the surface reaction rate controls. So, depending upon that, if you write that A plus S gives you A s and B plus S gives you B s, and then A s plus B s gives you some product species which is adsorbed R s plus S s, something like this, right, R s plus S s. Then this, if this is the rate controlling, this is your surface reaction step, then you will have a denominator n is equal to 2. So, this is the meaning of this step, right. So, there the rate drop will be faster, that is when the this adsorption, this step is rate controlling based on adsorption, desorption, surface reaction, then you will have a faster drop at higher concentration or higher partial pressure of these two species, which is shown here in the region 2, right, because this shows that the drop is much faster, and this simply says that it is a kind of the dual site or two species are reacting, and that step is the rate controlling or forming the product. So, this is what we have postulated from this here, that the term will appear in the denominator and its power will be raised by that number. So, how to verify whether the rate law confirms the experimental data or not, right? As I said, you need to do the design of experiments first, identify the number of variables, and to understand what should be the range of these experimental conditions, right, find out some optimum conditions, right, at which these experiments can be carried out further. So, design of experiments or factorial method will help you in that way. So, rate of reaction, I said that it is given by something like this. So, from experimental data you have made certain analysis, effect of partial pressure of each component, right, temperature effect, space time effect, right, and then you measure this rate, right. Now, this rate is to be verified from your experimental data, because this is simulated data, theoretical data analysis. So, now you have just linearized this is one method of this linear regression, what you call, right, linear or non-linear regression methods, when you have just R is equal to k p a to the power n. So, you can analyze the data by non-linear regression method also, just take all these combined R is equal to k p a to the power n, right. But if I take R a log of this R a is equal to log of k plus n log p a. So, that is a linear regression method, right. So, in that case it is expected that you are getting a line y is equal to a 0 plus a 1 x 1 plus a 2 x 2 and so on, right. So, you have linearized the equation. So, same thing something like here. So, this if you rewrite this equation, that can be P c minus P p P b divided by k equilibrium and divide by this R c, right, and that side you have the term which is your 1 plus k P c plus P b this divided by this. So, now this is a kind of equation which is in the linear form of this, right, and that is shown here, just like this y, left hand side is your y now, which is here, and that is equal to some constant which is because of this term 1 upon k a. Now, I have splitted it like this 1 upon k a plus k P c upon k s k a. So, cancels k a k, and third one is P b upon k s k a k d. So, it is something like equation in the linear form, right, because what is your least square method? You are just calculating the some error function, that is your objective function which you are defined, right, and you are minimizing the error between experimental and the theoretical value, right. So, and then you are just taking sigma for all number of data, right, and try to minimize the error, and where you get the minimum error or among all the set of data which you have taken, using that, and you can analyze the data and you can report the value of the parameter. So, this is what has been done in the linear regression method. So, this is what y, a kind of y, and this is your a plus b P c plus P b. So, how to do the experiment now? You have to change the partial pressure of C, right, keeping this constant. Same thing at different partial pressure of C, you will have data in terms of rate, right, and same thing second set you change the partial pressure of B and then keep this constant and again measure the rate, right. So, you can rate can be measured experimentally, observed experimentally, and these are known partial pressure and all the terms, and this is your thermodynamic equilibrium constant. So, that you can find from the or calculate from the thermodynamics of the reaction, right. So, every term is known in the form of y is equal to this, these are the parameters a, b, c, these are the parameters of the reaction. And what are these parameters? All of you know now, because 1 upon k s k is your small a, right, one parameter. Similarly, k upon k s k is the second parameter. So, it is basically 1 upon k s is your. So, your if you do this, so your B is simply 1 upon k s, right here. So, and then third one is your 1 upon k d k s k a, right. So, 3 that is the total parameter. If you look at these are k a, k s, k d, right, and these can be determined experimentally by selecting the proper experimental conditions. So, that has been done here, right, and once you do that, then you use the regression method, as I said, use the any software tool, right, or you can do analytically also depending upon the number of data available. So, but nowadays the software tools are available. So, MATLAB, like as I said, Origin, right. So, one can do these kind of regression, and thermodynamic analysis can also be done using these high size software tools which are available, right. So, nowadays not difficult. So, one can regress the data, and how to analyze this, right, how to decide the fit, whether it is reasonable or not, that you have to define some confidence limit, right, or say you decide some say 95% confidence of that whatever the data, if all the data fit to that 95% confidence, right. So, that is correct. If it comes to 90%, you have to generate further data or develop some change in the mechanism which can postulate more to these experimental set of data, right. So, if the fit is reasonable, then evaluate the constants and the parameters of the, that is reaction parameter. So, this is how the kinetics is done, or kinetic data for a catalytic or even non catalytic reaction is studied. So, you know the differential method of analysis, you know integral method of analysis for calculation rate of rate. So, the similar approach is being used once you have the mechanism and this kind of data, then RA can be calculated from those differential method or integral method of analysis, which I will talk little later very briefly. So, again how to optimize rate data. So, one need to understand about that, right, how to analyze a model and discriminate that, right, model discrimination. We have decided say adsorption rate controlling, desorption rate controlling, surface reaction, and even in the steps of the reaction it may be changing, right. So, you can have 1, 2, 3, 4, 5, 6 and so maybe n number of models, right, but ultimately you have to use that is discriminate the model where the error which is the most suitable or most theoretically fitting to your experimental data, and also verifying from the thermodynamics or the kinetics of the reaction, and then you decide the parameter of that reaction. So, just as an example I have just left it here to for your understanding, one can do that. So, suppose the rate of reaction, this is for the COCl2, right, phosgene gas, which is formed by reaction with carbon monoxide and chlorine, and carbonyl chloride is formed, right, and the rate of reaction which has been postulated and verified also is something like this type of. So, here you can see that this a square term here in the denominator, right. So, as I said, if first one can start with surface reaction as the rate controlling. So, here you have to say CO is adsorbing, then chlorine is adsorbing on the surface, and then these two adsorbed species are reacting and forming this adsorbed species, right, and this adsorbed species finally desorbs. So, this can be one mechanism, right. So, adsorption of this, then adsorption of this, and then these two adsorbed species are reacting and transforming into one adsorbed species and one vacant site, right, and then this vacant, this COCl2 star finally desorbs to COCl2 and star, right. So, adsorption, desorption, surface reaction, and as I said, most of the heterogeneous reaction, if adsorption is not controlling, then possibility is that this is controlled by the surface reaction. So, surface reaction one can also confirm here, because this is what the square, right. So, COCl2 star plus CO star plus Cl2 star is giving you COCl2 star plus this star, right. So, that may be a kind of surface reaction which may be rate controlling, right. So, one can very easily write the rate equations and then finally check whether it is matching or not, right. So, this is just for exercise, and sometimes we write this simple power law model also, because understanding the mechanism it needs lot of surface characterization, as I talked microkinetic model, right, and then you have to look at the surface characterization, IR spectra, proton and MR spectra, just to look at whether these species adsorb during the reaction or not, whether it is possible or not. TPR is one, right, TPD is one another. So, TPR, TPD can be done. So, by these information So, CO is taken on some catalyst, this charcoal, and you will feel that CO is absorbing on that, right. So, that confirms that yes, CO will absorb over charcoal under these condition of temperature, right. And same thing for chlorine. So, one can very easily check by doing the TPD whether this is happening or not experimentally, whatever you have postulated, right. So, one can look at that, and sometimes if you do not need this kind of details to understand what is going on in the reaction, then a simple power law model can be used, right, although not very correct from the heterogeneous catalytic point of view, right, but just one can correlate, because this value of k will be different than this one now, right. So, this is some kind of overall rate constant, which is a combination, which can be a combination of this like, right. And here again we have written in terms of the partial pressure of chlorine and partial pressure of carbon monoxide. So, with just a one can write it simply P A to the power A and P Cl2 to the power B and find out A, B and K, right, by linear regression or non-linear. But this is a just a this is true only for homogeneous reaction kinetics, not for heterogeneous reaction kinetics. So, actual mechanism cannot be understood from this one, right, but if the data are not available, the software tools are not available, time is limited, then one can use this also, and then one can find out the total mass of the catalyst required, right, for a given in this reaction, right. So, design of a fixed bed reactor, if you whatever the kinetic data you have obtained, right, or experimental data you generated, and then you evaluated the rate parameter. So, one can use that to, because the minus R is known, rate of reaction is now defined, and then one can look at sizing a reactor or the mass of catalyst required for a given conversion, right. So, that is what the meaning of design of a fixed bed reactor now, right now I am talking, right. So, I have already talked this part that you have a differential basically here when you look at the lab scale data. So, generally preferred one is the differential reactor, and I told you that the theoretically if you look at the conversion should be less than 10%, that is the definition of dispersion reactor. So, you should have a small diameter reactor with a small particle size and maintain the plug flow condition inside that, right. So, that is the neglect the axial and the radial dispersion. So, by selecting this reactor size, particle size, right, and high velocity of the gas, that is Fa, one can control this, right. So, once you have that information, right, or you have just selected a reactor and the experimental condition, and you know that when the conversion is taking place, then Ca will decrease down the length, right. Ca is the concentration of the reactant species, right, which is basically if there is a constant volume in the system, then it is Ca naught 1 minus x A. Just for a constant volume, you know that Ca is equal to Ca naught 1 minus x A, right, where x is the fractional conversion. So, it means if I write the data in terms of conversion, it will go like this, right. So, this is your conversion as a function of length of the reactor, right. Metal balance part I have discussed earlier also, just quickly I will go here, and all of you must be knowing now that the for a differential section your material balance equation is something like that, rate of input is equal to rate of output plus the disappearance because of chemical reaction and plus the accumulation in the reactant, right. So, for a differential section input minus output minus disappearance because of chemical reaction is equal to rate of accumulation, that is what the definition or for any reactor design or any system, right, you are writing a material balance, right. Input at any section, as I said before earlier also, Fa at this section Fa, and output is Fa plus dFa here, this is your output, right, rate of output. Accumulation we are assuming steady state, because the time you have to check when the conditions are not changing with time, and that is the steady state condition, right. The variation in property with respect to time is 0. So, that is 0 here, and rate of disappearance what I have written here, that will depend on suppose rate equation minus R A is the disappearance, and this is defined based on per unit mass of the catalyst, right. Rate of reaction can be defined in either many ways. So, in the heterogeneous reaction generally the moles reacted per unit time per gram of catalyst or mass which is reacted per unit time per gram of catalyst, right. So, either of the units can be used or definitions can be used, then minus R A here it is per unit mass. So, multiplied by the mass of catalyst. So, this is the total moles which is disappeared in this zone. So, one can write down expression because this cancels. So, minus dFA is equal to minus R A times dW from this equation, right, and equation will come minus dFA by dW is equal to minus R A, right. If you integrate this equation, because F A is changing down the length, right, dW is changing down the length. So, your equation in general is F A naught, because F A, you know, the moles F A is equal to F A naught 1 minus x A, right, that is input F A naught minus F A naught x A, which is the moles reacted, right. So, at any point this is the moles present. So, F A is the moles which is present at any point here, say z is equal to 0 or z is equal to z plus delta z, whatever, right. So, this has been written now in the form of F A naught 1 minus x A. So, equation gives you F A naught d x A, right, and that is equal to minus R A times d W. So, this is a differential form of reaction, and minus R A dash sometime we write here, which is representing that rate has been defined per unit mass of the catalyst, right. In homogeneous you define rate per unit volume of the reactor, right, here it is per unit mass of the catalyst, right, and based on that one can define, because mass of catalyst is related to the volume of the reactor, right, and times the void density of the bed, right. So, catalyst bed density sometime we call it, right. So, volume of catalyst multiplied by the bed density, right, and bed density will be catalyst density into 1 minus the void fraction of the bed, right. So, one can very easily define this density of the catalyst, that is as I discussed earlier, and based on the bed volume, right, when you are calculating mass of the catalyst which is given in a bed, right. So, volume will increase because there are voids between the particles now, right, that is bed void fraction I am talking, right. So, 1 minus epsilon b, if epsilon b is the bed fraction, void fraction of the bed. So, 1 minus epsilon b is the solid fraction there, right, that is the catalyst which is present, right. So, and if I define my density which is based on the mass of the catalyst divided by the volume of bed, this is the bulk density of the catalyst, right. So, these terms should be very clear to you, because sometimes different terms may be used here. So, when this catalyst has been placed in the bed like this, right. So, there is a mass of the catalyst which is m, suppose this mass, right, and the volume of this is the volume of the bed V b, because it includes the voids here, gaps, right. So, actual this volume of the bed is nothing but the volume of the catalyst plus the voids, right, that is which we are defining epsilon b, basically the void fraction of the bed, right. So, void fraction of the bed you can define in terms of the volume of the bed. Bed void fraction will be nothing but the if I say the void fraction of the catalyst epsilon b, which is the bed void fraction, right, and epsilon p is the pellet porosity, these are different terms, right. So, here if I am defining, so if I say that 1 minus epsilon b, or sometimes I write it phi also, sometimes I say phi also, which is a bed void fraction. So, some I will write it like this also in some cases, right. So, either you write epsilon b, which is now pellet porosity based on whole bed void fraction of the bed, right. When I say bed porosity, so basically it is based on the void fractions of the bed, right. So, that is mass of the catalyst if you define based on this, that is will define based on the density of the catalyst which is based on the bed, right, times the volume of the bed, right. So, density of the catalyst based on the bed means that will be equal to density of the catalyst times the fraction of the bed, like this, correct. So, basically this phi is the void bed fraction, 1 minus phi is the solid fraction, right. So, because you this mass of the catalyst, when you are saying the void should bed void should be avoided, right, but when you size a reactor, because the catalyst will be placed in the reactor. So, the actual side of the reactor will be larger compared to the volume of the catalyst. So, volume of catalyst, how do you do, what is the volume of catalyst? If I write just V c, that is mass of catalyst divided by density of the catalyst, right. This is the volume density of the catalyst density, right. So, that is important. So, it means when the epsilon p is the pellet porosity epsilon b is the porosity based on the bed void fraction, right. So, I will continue it next time. I stop here today.